Welcome back to a cloudy day in Thailand, and I think I'm almost over my man illness. And I wanted to bring you up to date after the last video. We now have all of this stuff to review. This is the Arduino Uno, which through some jumpers is controlling 6 relays, which bring 6 power resistors in and out of series with these 21700 battery cells. The purpose is to drain the batteries down to a specific voltage, and that's all going to be under control of the program running in the Arduino. Physically, everything is great. What I now have run into, and I didn't anticipate it because it just didn't cross my mind, is something that friends of mine, Newton and Einstein, also ran into trouble with, and that's called frame of reference. Now, people normally think of frame of reference in terms of physics, and with Einstein, it really comes into play when you're talking about really high velocities nearing the speed of light. That's when things get really weird and space-time starts curving and clocks start running at different rates. But if we think about things in an easy Newtonian space, a frame of reference is, say you're standing on the side of a road, right here, and a car drives by, like that. Your frame of reference is from here to the car, and the car is moving at, say, 100 kilometers with respect to you. You are stationary and the car is moving. So you perceive the car to be going 100 kilometers an hour. But what if you, say you're in Thailand, and you're on a motorbike with 3 of your friends and no helmets, sorry, I'll control my rant, and you are going the same speed as that car. You are also going 100 kilometers an hour. You're going down the road like this. Your frame of reference is now to that car will read 0, right? You are moving at the exact same speed as that car, so to it and to you, you're moving at the same speed. So how can it be both 0 and 100? But it all depends on how you look at it. And that is also where I ran into problems with my battery. So let me sketch that out for you. Okay, so now I'm going to walk you through some different scenarios about measuring voltage. Now, in the bottom line, what's voltage? Voltage is the potential difference in electrical potential between 2 points. And that's the key thing, is what 2 points are we measuring? So in this picture right here, we have one battery. Let's say it's exactly 3 volts. We have a voltmeter here, old school kind, with a meter that reads between 0 and 18. Right now it's not hooked up, so it's measuring 0 volts. We are not measuring any potential between our 2 reference points. Now, all I did was I connected the voltmeter across the positive and negative terminals of the battery, and we show 3 volts, exactly like what we would expect. Now what I've done here is I've added one more 3-volt battery cell, but I haven't changed the meter, so we're still measuring 3 volts because our frame of reference is only across this one battery cell. And what I did here is I moved the voltmeter to be across both cells, so our frame of reference is now the sum of 2 voltages, or 6 volts. Now, here's where we run into a problem, because the Arduino Uno cannot measure 6 volts. So in this scenario, we're going to blow up the chip. So let's see some other factors that come into play. Okay, now what I did is I moved the ground, the negative of the voltmeter, to the joint between the 2 battery cells. So now my frame of reference is only across one battery cell, and we're back measuring 6 volts. Aha! This might help us out. If I can somehow manage to get the Arduino to simply measure the difference in voltage across one cell, then I know exactly its voltage. Maybe if I put a bunch of these together, it might help us. Okay, here we have a more complex scenario, and please excuse my schematic. I'm not Big Clive here, okay? So we've got 6 cells in series, 1, 2, and then a bunch here, and then number 6. And I've got 6 voltmeters, and each voltmeter is only across one battery cell. This meter is reading 3 volts across this cell. This meter is reading 3 volts across this cell. And this meter is reading 3 volts across top cell number 6. So that kind of solves our problem. And so here's our problem. This is where Einstein and the makers of the Arduino come up and slap me in the face. The Arduino only has 6 analog inputs. So we basically have one connection to ground, and then we have analog input 0, 1, 2, 3, 4, and 5, which is going to be at the top of battery number 6. But by the time I get to battery number 6, analog input number 5, starting counting at 0, remember, that's going to be reading a full 18 volts, and it's just going to blow up the chip. So basically what my problem is I need 2 analog inputs for each battery cell, one for the top of it and one for the bottom of it. And unfortunately, the Uno can't do that for us. So what I really need to do is find another Arduino board that can tolerate 5 volts on an analog input and has 12 input channels. That's going to solve my problem. But that doesn't help me today sitting at my desk when everything that I need is in China. Because in the real world, this is how battery packs are wired. You have a number of cells in series, and the total voltage is equal to what your controller and your motor really want. You cannot run the motor of an electric motorcycle or a car off 3 volts. You've got to put a crap load of them in series. And that's why the iMax B6 is wired to handle this, because they have this so-called differential analog voltage signal sensors, and this cute little device, which I'll show you in a second. And this cute little guy is called a Cell-Log 8S, and if you can see in the darkness, it has the same kind of connector that's used in the iMax B6, and it plugs conveniently right into the same thing that I designed my battery pack from. So if we power it up, you can see the screen, and it's got a bit of a menu system. I've got it set for lithium ion, and now it's going to get very angry and tell me I don't have anything plugged in, and it's going to beep at me. So what I have to do is plug this in with the most negative terminal at the very bottom, and it immediately starts reading voltages. Sorry for the glare. So 1, 2, 3, 4, 5, 6. It knows I have 6 cells connected, and it's reading each cell because it's doing a differential analog voltage reading, which is beyond my grasp of the equipment that I have in my hand right now. This will be good when I've got the bike up and running. I will be able to just plug this in at many places in the bike and just do a quick sanity check and health check of all the cells. And if they're all within my particular tolerance, then I'm good. Otherwise, it's time for another bottom balancing session. So let's actually, ignoring all these problems, let's take a look at the functionality of how I've got the Arduino set up for me today. Okay, so let's take a look at the code that I've added. First thing I do is I set all the outputs to digital outputs for relay control, and then I turn all the relays off. I come down here. This is the same loop we had before about reading each voltage level. But then what I do is I come down here, and in addition to calculating volts from sample readings on the input, I also add an offset and then I multiply by a scale factor. And this comes into play for the calibration that I discussed in the previous video. And I'll walk you through how I did that. Then I come down here. Now this is where we're going to do relay control. I have a variable or a constant called drain voltage, which is 2.8. And if the voltage is above 2.8, then I turn that relay on. I set it to low, that fires the relay clicks on, brings the resistor into the circuit and starts draining power. If the volts reading is below the drain voltage, then I turn the relay off. And since this is all happening in a loop, we're going to get on, off as the relays cycle through and as the voltage comes down on each pin. Okay, we're up and running. The relays are all off and the voltages are all low. Now, what I've had to do is basically ground the input for number 2, 3, 4, 5, and 6, because when I put a battery on number 1, all the other ones float up to the point where the system thinks it needs to work on those as if they were real batteries, but they're not, and I find that annoying. I gotta see if there's a cause to that. But voltage input number 1 is currently functional, and what I'm going to do is put a battery across its terminal right now and listen for the click and watch the voltage here and the state of the relay. Click, voltage 3.494, and the relay is on. Now I'm not draining this particular cell because I'm only reading it across the analog input. It's not in the circuit with the resistor. But I'm going to take the wire off the battery. Click, battery goes off, and we're floating down to a low voltage level, and the relay is off. And we go on again and off. So functionally, the circuit works except for reading the individual battery levels. Now, let me go back and show you what I did for the calibration. Okay, in order to properly calibrate the analog inputs on the Uno, we want to take a bunch of voltage measurements, both with the Uno and my highly accurate fluke meter, or accurate enough as I need it to be. So I went into my box of goodies and I found a bunch of different types of devices that would give me power. I had a 5-volt USB jack, a 4-volt lithium battery, 3.9 volt battery from a GoPro, the 3.3 volt reference on the Arduino Uno itself, several discharged lithium batteries, a couple of AA batteries, and then a horribly dead lithium battery all the way down at 0.284 volts. So I measured it on the fluke meter and on the Arduino, and I figured out what the difference is between the two. And then I plotted that. Now, in a perfect world, the delta, the difference, would be 0, and if it wasn't 0, it would be a perfectly straight line. Now, what we're going to try and do is figure out a line that best fits these points. And I'm using LibreOffice, and it has 2 built-in functions. So with the slope function, you simply tell it the range of the 2 lines of data you want, so D3 to D15 compared to B3 to B15, and the intercept is the same. It's a different function, but you give it the same data ranges. Now what this gives us is these 2 numbers. The slope of the line, and if you remember back to freshman math, a line is yx plus b. So the slope of our line, it's going to be 1.031202. So it's just a tiny bit off from a slope of 1. And the intercept is 0.009987, which is just a little tiny bit above 0. So that represents 9.98655 millivolts of offset. So if we go back to the code, you'll see how I implemented putting this calibration line into the calculation. So I went back in the code and added a couple of constants. Scale is 1.0312, which represents the corrected slope of our line, and the offset is 0.009987, which reflects the offset of our line. Now, where we apply it is down here. After we calculate volts from the raw analog reading, I add the offset to the voltage, which is going to boost the whole line up by 9.9 millivolts. And then I multiply by the scale, which is going to bend the line up a tiny bit. And that's all we have to do. Once I applied the scaling factor and the offset to the code, the readings between the fluke meter and the Arduino were within a 1 or 2 thousandths of a volt. So this just shows the power of math and linear regression. So to wrap this up, we have a functional relay control system, but we do not have a functional battery voltage reading system. I need to go out and find a device that can handle 12 differential analog input readings that can tolerate 5 volts. So I'm off to find an Arduino that can do that, the big brother of this guy, or perhaps a shield that plugs in the top, or another device that I can connect to with the SPI or the I2C bus and then read those values across. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.